Okay, good morning, good afternoon, and good evening. And thank you all for coming for this presentation, Beyond Carbon, an engineer's view to addressing the climate crisis. I'm your presenter, Adil Saraf. I'm Technical Principal Asset Integrity Management for WSP New Zealand, based in Christchurch. Just a little bit about me before we start. So I have a bit of a varied background, the bridge engineer, moving on to refurbishing, managing them, and extending their service life, which kind of gives me a unique perspective of the challenges throughout the design life of a structure, and which has got me into this climate change topic that we're going to talk about today. So this presentation, based on some of the work that we've been doing in collaboration with industry, with HERA and Oricon, and we'll talk more about them later, to identify opportunities and solutions to reduce the carbon in buildings. And there's a couple of housekeeping rules. So at the end of the presentation, you will find a copy of the slides and other reading materials in the handout box. And please, during the presentation, do not forget to put your questions. That'd be great, so we can have a bit of a discussion later on. Okay, let's get the show on the road. There's a lot to talk about today, so you can read this later at your leisure. I'm really keen to get into it, but yeah, we're going to talk about how we're going to solve the climate change problem. So carbon and construction, this is the industry that we are in. You probably have heard or know, or hopefully you do know, that 40% of the annual global carbon emissions come from the construction industry. 28% of that is operational carbon, and 11% of that roughly is building and infrastructure materials and construction, basically the structural materials we use. And this pie chart here gives you a breakdown of the different sectors of the global CO2 emissions. And yes, there's another 10%. Just get the laser going. There's another 10% here. We're not looking at that now. That's for all the other non-structural components that goes into a building, but we'll probably look at that later. But for now, for today, we're focusing on this big chunk of carbon. Now, unfortunately, COP27 had identified that carbon emissions from buildings and constructions have exceeded pre-pandemic levels, which is not good. And there's an expectation that the construction industry will not meet the 2050 net zero commitments. Even though for New Zealand and other parts of the world have committed to having the net greenhouse gases below gross 2005 emissions by 2030 and achieving net zero by 2050. So we have a bit of a problem on our hands. So why does it matter? Well, what we do know is the climate is changing. It's a fact of life, resulting in extreme weather events, as we saw in New Zealand with the Cyclone Gabriel, and other parts of the world. They're also experiencing extreme weather events, especially flooding, which have devastating consequences. The solution is to reduce the volume of carbon being emitted. Now, there's a bit of a limitation on the way we're going with this. So the construction industry, based on my observations and what we're seeing, is currently focusing on carbon footprint accounting. And there's a lot of dependence on offsetting, as we saw in some of the government expectations on how their aspiration, how to address this issue. The limitation with these current pathways, well, first of all, the carbon footprint accounting. There are, the fact, there are just so many different rules and carbon calculators and ways of we can assess carbon from the ISO standard. ISTRAC-T have some great publications supporting documentations, but even brands in New Zealand, from Building Research Association New Zealand, have their own calculator, and you have OneClick, which is a commercially available one. Now, if you do compare all of these with the same building, you're going to end up with different results, even though the trends are the same. So the first issue I have is which one is correct. There's no standardized way or rules to follow. So you get different results. And the one is offsetting, and that's a whole topic by itself, but I'll just simply say that even the New Zealand Climate Change Commission urges us to address climate change and reducing carbon without depending on forestry and carbon biogenic offsetting. So we shouldn't depend on that. So again, you're probably all familiar with the different modules when we talk about climate change and modules A to D. Module A is pretty much the cradle to gate, and a couple of years ago, most of the focus from people you talk to, whether engineers and so forth, is how can we reduce the amount of carbon when we construct something, which is still a correct way. However, it gives you a bit of a skewed view of the world, because what about the other phases of the life of the structure? In the past year, there have been a shift, and now we're talking about cradle to grave, which is module A to C, which is all the way from building a structure until we dispose of it, deconstruct it, and demolition it. But we really need to consider also module D, because that's where, depending on what you're building with, is where the magic happens. And we need to consider the whole of life cycle, cradle to cradle. And it's really pretty much is what we're talking about when we talk about circular economy and so forth. So that's the phase that's currently a little bit missing in the opportunities there. So what's the opportunities? And this is from past 2080. 80% of the ability to influence the reduction in carbon is done at the concept stage. In my view, it's really late to start doing your carbon calculation when you've kind of designed a building at the design phase, which is here, because your ability to influence the reduction of carbon is significantly reducing. So we need to develop the tools, guidelines for engineers upfront at the early stages of design, or even when someone thinks of, I need to build something, to identify where the opportunities are, so that by the time you get to design stage, you have designed a very carbon efficient, reduced carbon solution. So how do we get there? iStruct have an awesome guidance out of the UK. Again, hopefully a lot of you are familiar with that, for the hierarchy of net zero design. And we're starting from here. You use less material, use lower carbon materials, and offsetting is like your final option, really. Now, the issue I have with this guidance, the hierarchy, is they start here with build nothing, which is easy to say when in the UK, for example, apparently up to 90% of the buildings that they require are already built. While for growing countries like New Zealand, but even North America or other countries around the world and developing nations, they still need to build. So the approach, how to get in and design something, changes based on what you see on the ground and what you have. It's still correct. I mean, if you do have an existing building, your first solution shouldn't be, I need to tear it down and build a new one. It's like, can I reuse it? How can I do that? And then you go to the following steps, from build less, build clever. It's all about efficient design, reusing, repurposing, and so forth. So what's being proposed in this project is, how can we develop, let's call it a New Zealand hierarchy or an alternative global hierarchy, whatever you want to call it, of net zero design, but by embedding what we're terming the 4 R's, which was the repurpose, refurbish, reuse, and recycle. Pretty much developing the guidance so engineers enter a project with those 4 items, the 4 R's, already at the back of mind and at the basis of all design. Which then results in, how do you achieve, so when you have an existing building or an existing structure, you call it a brownfield, for example. So your first question should be, can it be repurposed, refurbished, or is member dismantled and reused? But if you do have to build new, then it's a different problem. How can we design to allow for future repurposing, refurbishing, reuse, and recycling? At the moment in New Zealand, we design for 50-year life, but we should design for longer, even 100 plus years. How do we consider designing for 100 plus years then? That has its own challenges. Should we base the decision of the structure's importance level, which is a function of the expected loading, especially wind and seismic, and the probability of the occurrence, which will affect how we design, and the load that the building is expected to encounter over its life? How do we deal with durability? What about fatigue and seismic design, especially fatigue, as currently all the stress curves are based on 100-year life. So we have to update and revise our design standards to allow for that. How do we cater for new structural systems such as steel timber hybrids or modular systems? And really, anything we do from now on, we need to maximize waste minimization and offsite construction. So we have a problem. How are we going to solve it? So in collaboration, so Heavy Engineering Research Association, HERA, which is in New Zealand, and it does a lot of R&D for the steel industry in New Zealand, has partnered with WSP and Oricon. to develop a solution. And we have an industry advisory group, which includes MB, the Ministry of Building Innovation Enterprise, brands, the Structural Engineering Society, CSOC. We also got Concrete NZ, the Timber Design Society, and the Timber Design Center. Pretty much what we've done is we've teamed up with the three main construction materials, steel, timber, concrete, the Engineering Society, anybody who's anybody in New Zealand, to develop a solution. And what we're trying to do is developing a material agnostic design guidance manual. And as well as the output from this project is recommendation for the changes to the current regulatory framework to allow and realize those opportunities to reduce carbon in construction. At the moment, we're focusing for all engineering practitioners to design low-rise, low-carbon buildings. And we're going to take into account the whole of life cradle to cradle life cycle assessment, module A to D, so not just module A or A to C, it's the whole of life. We're also looking at the New Zealand Building Code and identify what the opportunities are. So we're looking at the different clauses, in this case, clause B for stability, which includes B1 structure, this is related to the design, and B2 durability. We're also looking at moisture and high energy efficiency, and as well as the focusing on looking at reducing operational carbon, which I've identified that not many people are really taking that into account. And what is the contribution of the building substructure? I've heard examples where someone went and designed a beautifully net zero building. However, their foundation is so full of concrete that you would never actually make up for that carbon spent there. So there's a bit of a disconnect because substructures are out of sight, out of mind, and sometimes they're not really considered. So what's the methodology of this research? We're doing a literature review, of course. We're benchmarking selected existing buildings. So all the buildings we've looked at were built by 2020. So they're actual buildings, and we've done an industry survey. We have design examples, carbon footprints, and based on the findings, we used a selected benchmark building to consider different materials, steel, concrete composite, concrete, steel, timber hybrid, and so forth. We're playing around the grid layout to try and identify the most efficient layout for the material in question. What are the effects of different seismic zones, soil condition, and so forth in a building design, with the aim of identifying the optimal design parameters to achieve the lowest embodied carbon, take into account all of the structures, life cycle module A to D and the New Zealand Building Code clauses. We're going to undertake a carbon footprint analysis for the developed examples, comment on the impact of other life cycle assessments, which apparently, again, are not really considered, especially costs. If you change your solution, what the cost will be. And the other big question is it actually available? There's no reason. I've seen examples where someone went and designed a beautifully low carbon solution, and then they went to market, and the contractors came back and said, we cannot buy this stuff, or it's very expensive. And of course, we're going to end up with a reporting about all this. Finding today. Okay, this is the new bits. So this here is our steel concrete composite building. This is one of the examples we've done. This is for the superstructure. We then went and redesigned it for, and I do have to say for the steel concrete composite building, it does have a concrete shear wall as part of a seismic system, seismic restraint system. We then redesigned that for a steel timber hybrid, but still with that concrete shear wall. So you can see there was a slight reduction. And this is excluding module D and biogenic carbon sequestration. We'll touch upon that later. Now, we've taken our steel concrete composite and we removed the concrete shear wall and we changed it to a moment resisting frame, and you can see there was a significant reduction. And we did the same thing and put an eccentrically braced frame. So we're basically seeing what the influence of the seismic restraint system on the design, and there is a significant reduction. But then if you look at the hybrid, the steel timber hybrid with the eccentrically braced frame, that gave us the lowest solution. Now, again, there's something more magical happen later on, you'll see with the solution here. But you can see, depending on the different seismic system you've used, introducing timber, you do end up reducing the superstructure global warming potential. Now, this is not it. And as of yesterday, we now just introduced the same building in reinforced concrete. replace the whole thing reinforced concrete, and the intention now is to talk to concrete instead and see, okay, how could we reduce carbon from concrete, looking at different mixes and so forth. And then we're also going to talk with the timber people and also develop with them a timber solution to have a full picture. And this will all be published later. Another thing we want to look at, as we said before, is substructure. And we've developed this flowchart, and the whole intention of it is give the engineers the right questions and tools to ask for the geotech, understanding what the different solutions, whether for shallow or deep foundation, and what their carbon potential will be. And in some situations, it actually may be simpler to say, actually, your site is so bad that no matter what you do, you're never going to recoup that carbon, so you might as well select a new site. So again, this could be a tool for even developers up front to go in and say, actually, am I building this building in the right location? Now, why are we looking at substructure? Because what we've assessed, depending on the soil condition and so forth, the carbon emissions from the substructure could consist of 40 to 60% of the total amount of carbon when you take the sub and the superstructure together. So a considerable amount could be in the foundations. It's another great opportunity for you to identify early on and save on carbon there, not just focusing on the superstructure itself. Now, this is the big one in my view, and this is where the biggest impact can be, and it's basically the carbon from operational carbon, electricity use effectively. So the first graph here is looking at a lot of countries. We still have boilers and air conditioning, so it's not just New Zealand, and there's been quite a bit of a shift of replacing those in New Zealand. And if you take the building that we have selected, this is the amount of energy, CO2, to be used over its 50-year life. Now, the issue we found in New Zealand in the building code for clause H1, which is related to thermal insulation, is actually allows for thermal bridging. Now, again, this is not an issue in other countries, but in New Zealand, we have that issue. And you can see that a significant amount of energy being spent because of that. Now, if we introduce thermal breaks in our buildings, we can reduce that carbon and energy consumption significantly, more than half, just by putting a thermal break. Now, this is the old H1 rules, which again, technically speaking, the building was built in according to the standard of the day. And in 2023, the building code H1 insulation rules have been updated. They've actually doubled or even tripled the amount of insulation you need to do, the R values, to reduce them. But the issue we found is still allows for thermal bridging. So the big surprise for us, well, if we introduce a thermal break, which again are readily available from overseas, we can bring them from New Zealand, from UK, and effectively, the simplest thing I can explain it to you is you have a steel frame and you have a balcony. So when your steel beam of your balcony is basically in direct contact with your steel frame, what that does, it allows thermal bridging, and that means that your air conditioning, your boilers, or so forth, have to spend a lot of energy to address this cold air, the cold transfer of cold or heat, and condensation and so forth. So by simply putting a thermal break between the balcony and the steel frame, a structural thermal break, you can address this energy just by doing a really simple thing. And you can also go back to using the old H1 rules as well, which also reduces the amount of embodied carbon. Now let's take that a step further. And again, this is something for not just New Zealand, for the whole world. What happens if we update and change our boilers and air conditioning to more efficient heat pumps? So even in just going to heat pump from the beginning and assuming the old standards and allowing for thermal bridging, we have reduced it significantly. So the simplest solution here is get rid of your boilers and air conditioning and use more efficient heat pumps. But again, if you introduce the thermal break, that reduces significantly. The old H1 rules is also not too bad compared to this, but it could be better. But again, what we're saying is if you use the old H1 rules with the thermal break, you can have a significant reduction compared to what we're having now. Now, this is all great. Quick solutions, superstructure, substructure, and operational carbon. But what does it mean, and how should we look at it when we look at a whole of life cycle assessment and put it all together so that it can really impress and show what the opportunities are? So we put a pie chart. So this is all the carbon that this building from operational, which you can see is a significant amount compared to the superstructure and substructure for our steel concrete composite building. This is our reference case with boilers and air conditioning, what we used to do. And you just look at this here, and the first thing when you look at it is say, hold on, there's a significant amount of carbon over the 50-year life of the building from operational that's significantly greater than what we're putting in for the superstructure and the substructure module A components. So what we did, we had the A to C, and give you here around 1,564 kilogram of CO2 equivalent per square meter of this building. The building was around 1,755 square meters. And if you take module D and any biogenics, that give you a little bit of reduction. But in this particular case, we have steel and concrete. But again, the first thing you'll see is I need to reduce this. Now, if we take into account our steel timber hybrid, even though from a superstructure, your frame has significantly reduced, especially when you take biogenic, if you look here, it's 109, been reduced from 261. Sorry. Again, it's like, wow, we've reduced the amount of carbon, but you still have that significant amount from your operational. So the next solution is, okay, we're gonna put the thermal break, H1 rules in the old building. Even if you take your steel concrete composite building and reduce your operational carbon, that is already there a 50% reduction in carbon. And you haven't done anything different from what we do at the moment. But the beauty of this method is now you can say, okay, I found this big operational carbon emission here. I've reduced it significantly. I've achieved 50% reduction. Awesome. This is an easy fix to do. We can do it now. But I really need to reduce now the next big thing, which is your superstructure. And that's where going to a steel timber hybrid with a better seismic retrain system, you've reduced it even further. And you can see here, this is when the biogenics are taken into account. You can see here, we started with 1,473, and we reduced it by 2/3, effectively. So the next step, again, when you have a look at this now, you say, oh, now I need to reduce my substructure carbon. So that's your next challenge. But you can see by changing the perspective of how we account for the carbon throughout the life of the building, you can quickly identify now where the big opportunities are, and then you go down the hierarchy of this is a simple fix. I've reduced operational. Let's go to a steel timber hybrid. That's awesome. And next step is how to reduce the concrete contribution. Again, I don't have the answer now, but that's coming up next later on in the report when we issue it. So lessons learned so far. Target the easy ones to achieve 50% reduction for 2030 for new buildings. From New Zealand, install thermal breaks, which also allow the use of the old insulation clause H1 provisions. This in turn will assist in reducing the upfront module A embodied carbon as well from reduced insulation. If you have that in your country, if you already use thermal breaks, you're better than us. You're halfway there. So your next solution for you is to replace your old use heat pumps for both heating and cooling. So go to a more energy efficient heating and cooling system. That's an easy win. You can reduce 50% operational carbon of your total embodied carbon just by doing those. For existing buildings, convert to a more energy efficient heat pump for boilers and replace boilers and air conditioning. Increase your insulation levels with the aim of reduce energy consumption. Again, this is something you can do now. Parallel to that, to achieve greater than 50% reductions by 2030 and net zero by 2050, we need to design for ease of repurposing, refurbishing, reuse, and recycle, designing for longer life with durable, low maintenance components, and designing with more efficient, lower carbon components. Now, the good news is, whether it's steel, concrete, timber, whatever, they're all heading toward those net zero or low carbon components. Every day we hear new development in technology that allows for, net zero steel, low carbon concrete, or net zero concrete. The expectation from what I've seen, those solutions will be commercially available, are likely to be commercially available post 2030, between 2030 or so. So it will definitely be there by 2050. But what do we need to do now? And now is let's save an operational carbon to achieve 50% reduction. But how do we achieve those greater than 50% reduction for engineers? Now, how do we design for repurposing, refurbishing? Because everybody said it's easy, it's there, but it's actually you need to provide the guidance to do that for the engineers. So what we've developed is this framework. Now, this is the vision, and hopefully next year, late next year, it should be a reality. Imagine you go to a website and you say, I have a building, and you start here. I have an existing building, and it takes you down this pathway. And basically, it tells you if you're repurposing, refurbishing, and you click on each one of these boxes, and it tells you what you're up. Basically, it takes you to this matrix, which is currently being developed by Hera, and basically tells you, okay, here are your solutions. And each one of these solutions can have the X amount of carbon potential reduction, X amount of costs, or this will how much is available or not. But if you're going through a greenfield, a new building, well, what about if you design for 100 years? Then you have to, the way you design it is with the focus of repurposing and refurbishing, and at end of life to reuse and recycle no matter what. But again, you then enter what we just talked about. How do you approach a substructure, superstructure in the envelope, operational carbon, and what the effect of each one of those is on the next one. All of that will be provided with this website. So imagine by the end of it, you went through your pathway, you clicked your software selection, you get issued a design features report to reducing carbon. That's what we're aiming for, and that's what we're currently developing. And the vision of this will be not only a hard copy, but also a website for people to easily use. So in conclusion, decarbonizing the construction industry is our challenge of the century. Individually, the changes we make may appear to be minuscule, but together they add up, allowing us to reach our 50% reduction target by 2030 and net zero by 2050. It's an exciting time for innovations, which our industry is well placed to deliver solutions that will drive down emissions and help lessen the impacts of climate change. This presentation highlighted the current limitations and proposed solutions throughout the development of a New Zealand hierarchy of net zero design, while we're also developing a material agnostic design guidance manual, and we're also the recommendation for changing the current regulatory framework. We're going to have a discussion with embodied in the next couple of days about the H1 clause, for example. And together we can create a greener, cleaner, and sustainable world for future generations. Thank you.
Thank you, Ryan. Fantastic presentation. I will just mention quickly the housekeeping items. The presentation slide, along with some PDF from a recent paper from Ryan, is available in the handout box to download from the GoToWebinar control panel. And also, please continue to log your questions in the question box on the GoToWebinar control panel. We have just a few minutes. I will start reading the first question. What are the next steps in this research, and when should we expect the final report to be issued?
Yep. So the next step, the aim by Christmas, we're actually going to write up 4 different articles that delve into greater detail, the stuff, all the numbers and behind the substructure, superstructure, operational carbon, and the framework in much greater detail. Those will be published in engineering journals and by Hera, so it'll be online and engineering journals in New Zealand. But if you are overseas, you can get them online. And the report will, all going well, by October next year, the final report should be out. So there's not much. I know people say, oh, it's next October, we have a whole year. It's actually quite a lot of work, but the focus now is to finish all the calculation parts and get those articles going so we can get public feedback and get those messages across.
Thank you. You mentioned the current work is focused on low-rise buildings. Can you please explain why and what about other building typologies?
Yep. So in New Zealand, 80% of our building structures are low-rise buildings. So we thought we'll focus on that because that will have the biggest impact. But this is the vision again, is we have multiple design guides for different building types, different typologies. So we started with the low-rise because that had the biggest impact. But later on, we developed one for medium-rise, for high-rise, probably for warehouses and so forth, because the expectation is depending on your building type, the rules will change. So so far, honestly, I think for low-rise buildings, there's not much of a case for 100+ year design life, but that will probably be much more important for a high-rise building. So the intention is let's just get this base work ready and correct, and then we develop over the next few years other building typologies as well.
Thank you. Next question is about renewable energy. There's currently a shift to renewable energy. The question is, wouldn't achieving net zero electricity make the operational carbon argument obsolete?
Yep, I've already had that from someone the other day. In theory, so in New Zealand, we're already relatively low carbon electricity grid. I think over 80–90% of our power is already hydro and renewable energy, except for Transpower, which is our energy distribution organization company in New Zealand. They themselves in their report said by 2050 we need to have an additional 30 gigawatts amount of energy power generation, which we don't have now. So we did the numbers. So in theory, if you, let's say, for argument's sake, you went and designed them all out of wind turbines and they're very efficient, the wind blows all the time and so forth, we would need pretty much 90 new wind farms, of which each one has around 30 or so turbines. That in theory, all that carbon spent to build them, because the wind is very net zero, it will recoup the carbon quite quickly. However, the issue is not that. The issue is cost. To build that much power generation for New Zealand, back of envelope calculation is around $26 billion. Where are we going to get that money? So what we're saying is there are simple solutions that you can do now, very cost-effective solutions by insulation, thermal breaks, that will delay or reduce the amount of new power generation needed when we shift to heat pumps. So yes, this argument, in my view, does make a lot of sense, because it's not just about achieving net zero, but it's also being able to afford it.
Thank you. The next question is, how do you apply this for infrastructure design when we cannot change the building location and not being the main designer?
Okay, so if you go into an existing building, yeah, I think the first thing you should do is just look at the building. Refurbishing building is commonly done overseas. From a New Zealand context, is your insulation okay? You can do that. You can gut the building and put new insulation. I appreciate thermal breaks will be difficult on an existing building, but get rid of your boilers and put heat pumps. So it's really talk to your mechanical engineer to see where the savings could be made in that way. There's a building in Auckland, the old Auckland Council building that's been refurbished. It's a 1960s building that's been fully refurbished and given another 50-year life. So it is doable. But yes, I appreciate there are difficulties. But that's the whole purpose of this report as well, is we're going to explore what are those challenges are and how we can deal with them. And we will go out to industry for feedback such as this and what your challenges are so we can address them. So it'd be great if you can contact me later.
Thank you. Just due to the time, I will take the last question. Do you believe that this research finding is applicable to other countries besides New Zealand?
Yep. So again, if you're like say in the UK, you already build buildings with thermal breaks. That's awesome. We're going to go to the UK to get your thermal breaks to install them here. But the challenges in the UK, for example, is there's still a lot of boilers, I believe. There's still, there's not much air conditioning. But it's interesting because the UK is all focused around heating, but the shift will be at some point regarding to cooling, as you have your hot summers. So yeah, again, it's all about how do you keep your building warm, cool, with less energy. So that part will be applicable worldwide. We are learning from the UK, for example, but other countries in the world, especially that are still growing, they will probably benefit from this as well, as the guidelines are based on engineering first principles on how do you approach a building and how to design it from a new or refurbishing.
Fantastic. Thank you, Red, for a great presentation. Thank you all for joining us today. All additional questions that were unanswered will be answered directly by Red. So thanks again for joining us today. Thanks, Red.
Thank you.